All right, so we are technically in the session of shape memory polymers. You guys just conducted the part A lab session on making shape memory polymer or casting them. And remember, we talked about baking them in oven for 6 hours, and then you could see a result this Thursday. So the polymer, the shape memory polymer you were offered last class was one category called thermal set. So there are two types, vaguely speaking, two types of thermoplastic. So the one you use are thermal set. And the ones I'm going to introduce today mainly focus on the other type of thermoplastics. But both have shape memory effect. The difference is, PLA ABS filament, like you would often heard when we do 3D printing, those types can be melted and then extruded and then solidify again. So they are more common thermoplastic, especially for additive manufacturing, the fused deposition style additive manufacturing. And thermal sets, on the other hand, are not meltable. So they can't transition from a solid to liquid phase. So that's why you have to use molding and casting, right? We add in a cross-linker, and after a while it becomes stiff. That's the end of the story. You could soften it so it looks rubber-ish, but you can't convert it into liquid that easily without using organic solvent, etc. So it's not possible with those conventional fused deposition printers such as Ultimaker, MakerBot, Prusa, etc. But it's possible because the polymerization process can be controlled by cross-linker. So it's possible with those kind of UV curable method in 3D printing. For example, Formlab is a stereotypical stereolithography printer. They use UV light to cross-link those thermal sets on site. Anyway, the core message here is that a majority of the thermoplastics, no matter if it's epoxy resins or the normal 3D printing filament, they all have shape memory effects. And it's actually quite of a universal phenomenon. And it depends on the type of thermoplastic. You might need different way to process them, different way to control the shape memory behavior, but this vastly exists. And it's also very widely used for different industry, including medical industry. So for example, if you want to deploy a stent to support your vascular system, for example, sometimes people inject something really small. And then once they touch upon the body temperature, they are shape memorying, right? They will blow up into a larger structure to create a scaffold on site. So you can see in this case, it's basically a self-deployable structure. You can program them to be smaller as a temporary shape, and with the right condition, they can blow up. And also the triggering conditions could be different. So Ke showed you last lab session, this thermal set that responds to temperature. Temperature is about 60 to 80 Celsius. But you could also find polymer responding to body temperature. And some are even responding to room temperature, 30 Celsius. And you can also find the ones responding to different stimuli rather than temperature, could be pH responsive, for example. So this is the official, one version of the official definition of, actually, just bear me, I need to, okay. All right, so this is the official definition of shape memory polymer. So they are polymeric smart materials, have the ability to return from a deformed state to their original shape when induced by an external stimuli such as temperature change. So again, from the lab session, what you did is you are programming a permanent shape state by molding and casting. And then in this Thursday, you will be able to, with your hand, deform the shape into a temporary shape and then observe how it can recover back to the permanent shape. And just a little bit of a polymer science. So what's happening if you look at the very top? So you casted the shape into a permanent shape. But then you can heat it up, just heat it up to 60C, for example, for the polymer we are going to use in the lab session. And then deform it in any way. In this case, it just stretch it straight. Now you have to hold the polymer, let it cool down. So once it cools down, the polymer will stay straight in room temperature. And we call this temporary shape. And then once you place this back in hot water or back in an oven, basically give it extra heat, it'll remember its permanent shape and recover back to its permanent shape. So again, we mentioned temporary and permanent shape terminology last time in lab as well. And here I'm just giving some extra information. And if we zoom in to the molecular structure, this is also quite common in most of the thermoplastics. So again, if you look at the left column, the red polymer chain. So in a permanent state, so all the polymer chains are entangled. And one of my material science student mentioned this looks like a spaghetti. His analogy was spaghetti. So they're all entangled, they're randomly arranged. It's preferred energy state, but then you can always force it to align themselves in a slightly different way. So look at the middle blue one. So this is when we stretch, right? When we stretch the thermoplastic, when it's under a raised temperature, elevated temperature. So they will be forced to go straighten. If you think about against spaghetti, now you are stretching it longer and it's more or less aligned with each other. And then the color represents the temperature states too. And then you have to hold it and let it cool down. That's why it shows as blue. And then it'll be forced to stay in this sort of a, straightened mode. And energetically speaking, this is not its preferred state. It doesn't have its lowest entropy more of a material science terminology. And then if you now give it extra heat, look at the most right one. So the polymer chain will bounce back. So if you raise the temperature again, it will bounce back because this is its preferred state. The preferred state is entangled, randomly arranged. And that energy balance basically microscopically dictates this shape memory effect. And there's also a very important concept. We talk again and again, we will. That is its glass transition temperature. So those thermoplastic has a specific temperature. Below those temperature, they behave like a solid. And above the temperature, they get into more like an elastic rubbery state. So, and TG is important because if you want to switch a shape from temporary to permanent shape, or if you want to, choose a temperature to trigger the shape memory effect, you need to make sure the temperature is above glass transition temperature. That is when the polymer gets softer, so it actually unlocked and can have the bandwidth of basically recovering back. And again, so the core message is there is a temperature, short name TG, and the TG, which is called glass transition temperature, is important because only above TG you can get the polymer to be softer enough to morph, to transform. And some of the examples, we showed repetitively in the earlier class. I brought them back just because I want to share some of the more detailed insights in terms of how this is working. Now you know the basic concept of shape memory, plastics. So a lot of the morphing methods we did in the lab in the past belongs to shape memory thermoplastic. So you could handle it by molding and casting, as I said, but also you could handle and program the permanent or temporary shape by more advanced digital manufacturing methods, such as 3D printing. So this is an example. Basically, you print a flat sheet, and once you put it in water, it self-folds into a chair. So in this case, you might as well say, The flat disk is a temporary shape, but once you put it in water, basically once you give it extra heat, hot water, it'll recover back to its permanent shape, which is the shape of the chair. So all of you guys perhaps have experienced this failed printing experience out of an Ultimaker or similar desktop 3D printer, and it's called warpage. So the idea is if you print too fast, or if your printing substrate is too cold, sometimes the filament doesn't stick to the substrate well, right? And even if your first layer sticks very well as you are printing a taller and thicker structure, sometimes the structure just automatically pop off the printing bed. That's why sometimes you use glue tape, you turn on the heat to avoid this phenomenon. So this warpage effect, which is kind of a defect of those low-end 3D printer, is also due to the shape memory, or at least the polymer chain arrangements within the filament. So again, as I mentioned, if you buy a off-the-shelf filament from Amazon, for example, the polymer stays in a relatively random chaotic mode by default. And when you melt the filament and started to travel it through this very narrow nozzle, you are forcing the polymer chain to align themselves. So they go straightened as they are being deposited on the printing platform. But as I mentioned before, this straightened mode is not as preferred. It is kind of a temporary shape, in this case, programmed by the 3D printer nozzle, not by your hand, but it's still a temporary, not preferred state. What happens if you heat the printed structure? If you heat it up, so the polymer chain will try to go back to its random mode. And as a result, the printed structure will try to shrink along the direction of the printing path. So again, this just repeat what I just said. When you print the filament on the printing substrate, it will go straighten, but it doesn't like it. It want to go to its random mode. So that's why when you heat it again, so the polymer chain will bounce back, and macroscopically speaking, you see the printed trays getting shorter and fatter. And there are many parameters in the printing process can affect how much it will shrink when you heat it up again. So that includes, for example, the printing speed, also the individual layer thickness, etc. And you can do something smart about it. So in this project I'm introducing here, we're trying to turn this so-called defects of those very accessible thermoplastic filament into a advantage. Basically, if you print those shrinkable PLA filament, for example, on top of another plastic substrate that does not have this shrinkable effect. So for example, if you print PLA on top of a TPU material, both are very accessible online, right? And you can form a bilayer because you think about the top surface will try to shrink, but the bottom doesn't. So as a result, the structure will bend. So now you created a bending bilayer actuator per se. So basically, you can go from there to really tune the bending angle. Bending angle, there are many, like I said, many parameters of the manufacturing process can dictate the bending angle, but the easiest is actually by length. Just think about it, right? If uniformly they bend to the same radian or curvature per unit length. Now, if you try to just increase the length of the actuator region, actually it just accumulates a larger bending angle. So if you look at the table on the right, we show you could actually control the bending angle by simply changing the total length of the bilayer region. And from there, you can really start to think about more interesting shapes. Bending is so important. And I know some of you guys really love origami just because a simple mountain valley fold can form very complex shapes. Actually, mathematically, it's proved just by folding up and down, you can build arbitrary 3D shapes like a bunny. If you spend time, you can use your hand to just fold things into a bunny. So in our case, the same. Once you started to be able to control bending angles at any arbitrary location on a flat surface, you could start to morph a flat surface into also any arbitrary shapes. So here you can see a flat disk we printed can turn into a quite complex rose flower that bends inwards, outwards when you heat it up. So this is all the hidden layers. At the beginning, we did not have any, so-called inverse design or sophisticated computational tool. Everything was done very manually. So it was actually the flower was designed iteratively by a few industrial designers who basically had a very minimum coding experience. We were just using a commercial slicer, but as you can see, it's a very detailed printing process. So a simple white disk looks like a single layer, but actually has about 8 hidden layers. And within each layer, you have different printing direction, printing speed, and also whether it's TPU or PLA in order to control, think about it, right? Control the bending angle and bending direction. Think about it, if you put TPU at the bottom, PLA on top, it will bend upwards. And if you flip the order of the PLA and TPU, it will bend downwards. So there are many sort of very fun, actually, control parameters you could tune very manually. And I believe the Taoye, who actually made this flower happen, had a lot of fun. But then we soon also realized this is very sophisticated. It requires a lot of patience, time, and perhaps also a bit of a talent and gut intuition of a senior industrial designer or product designer here, or designers in general, let's say. So we started to see, the necessity of developing a tool. And there were more material science researchers got involved in the project. And it basically shows it's a tool. You start with a flat shape. You, in the tool, can choose which area you want it to bend and bending to which angle. And the tool will simulate the effect. And if you like the folding effect, you can export the digital printing file. And this navigation shows the compositions of layers and also the printing direction of each layer. And from there, you can export a G-code, which is compatible with most of the mainstream desktop 3D printer. So this goes into one of the agendas, at least in my research group. So we're trying to democratize some of the morphing method design, and a computational tool and also, the fabrication strategy are critical to the idea of democratization. So talking about why we are doing it, it's a very young field. People are still trying to figure out what the technology can do for different fields. For example, in the context of advanced manufacturing, if you guys have, I believe actually a large portion of you guys had experience printing similar structures with a desktop 3D printer. So if you print this rose, you can imagine you need a lot of support material. And also because the shape is intricate with a lot of voids in the middle, you will end up very kind of rough surface textures, right, as you are removing the support material. And this will take about 8 hours to print. And I don't know how long it's going to take you guys to remove all the support perfectly. It took us about 30 minutes. So if you want to use this 4D morphing method to print a flat disk, then you only need an hour. And there's pretty much no post-processing time because all you do is to put it in water and trigger it on the fly. There are, of course, all these experimental technology come with shortcomings. Right now, you could imagine the folding process depends on the accuracy of your triggering conditions. Could it be less accurate than directly into the 3D shape to print? So you want to started to think about that more seriously if you started to get very serious about, domains that require shape accuracy. For example, if you're designing a car engine, we actually had a experimental project with Honda. So they came in and wanted to do a car engine cover because in their shop, in a car company, they iterate a lot on their different covers and shapes and everything within a car, outside of a car. And it's very expensive to do the iterative, basically prototyping. So they want to explore this method. But we got some excitement, but also a lot of challenges, because like what I said, this method may not be as accurate as conventional way of doing 3D printing. And that becomes critical for those industrial settings, like a car, right? Or like a medical device. Something get into your body is supposed to fit perfectly to a particular person's heart or vessels, but it didn't. So these are all the very hard problems the field is trying to solve, from the material development, from the computational tool and the more accurate physical-based simulation, etc. But at least the vision is there. So if you talk about 4D printing for advanced manufacturing, you can also consider this as a quite of a sustainable manufacturing process. We're all under the stress of climate change. We really want to save energy and materials, right? Here and there, in all, honestly, all the way we live, we transport, we make, we grow, we eat. So this, as you guys can tell, save manufacturing time, save manufacturing materials. If you flat pack them, like how IKEA is packing its furniture, can also save packaging space and transportation effort and transportation space. And because it's self-assemble, you could also have save assembly method. So the dream is there. And this also gets more practical maybe. If we think about constructions in extreme locations, such as on the moon, you guys, I was just in a workshop organized by NASA. They were very serious about building, first of all, they're sending astronauts to stay on the moon, right, for a couple of months, I think this year. But then they are also quite serious about long-term citizen-based habitat. And they are literally, this is relevant to our class, this time, they are deploying a soft goods inflatable tent, pretty much, to host astronauts. Again, because packaging space and also weight of the structure is just so critical when you think about space travel. And I'm glad to see inflatables on the moon. Actually, this is really happening. But again, back to those flat pack manufacturing method and on-site self-assembly methods, those are critically important when you think about basically construction in extreme environment and also the transportation limit. So that's a one story along the line of shape memory. These indeed are shape memory, legitimate shape memory effect of a very accessible thermoplastic. And you could, in the lab, the students, actually Zhenzhe was part of this, also explore more of an inverse design process. And again, if you come from a CS background, maybe this is more of in your point of interest. So you could process a arbitrary 3D shape into a flat disk, and then you can print it and let it fold back into the input shape. So the idea is if you have a bunny on the top left corner, you can simplify it into limited numbers of mesh. And then now it's unfoldable. It's like a piece of origami. You can also calculate the bending angle needed for each hinge. And then you can, right, address the corresponding length of the bilayer actuator introduced earlier. And then you should predict a very similar folding phenomenon in the physical world as if in the computer. I likely gonna try to go very fast on this part. If you are lost, that's okay. But if you're interested, check the paper or reach out to me. But the idea is there are very mature, basically flattening algorithms. So when you deal with the arbitrary shape, how you flatten it and how do you calculate the bending angle needed at each hinge, those are known knowledge in the field of computer science, especially computer graphics. However, when you try to leverage a traditional origami folding algorithm for those shape memory thermal plastics, you want to deal with the fact that those plastics don't fold sharply, right? If you fold a piece of paper, you can create a very sharp hinge. That's what's shown on the bottom left corner. But when we are replacing the sharp hinge with a actuator, with a smart actuator, suddenly it's not the sharp folds anymore, it's a curved folds. And we need to geometrically accommodate the length needed for the folding region. So that's why, rhythmically speaking, you have to do an offset of the area size of each face to accommodate the length. Again, it gets actually quite interesting, but also quite simple. If you're interested, we can definitely dive into this deeper in a separate conversation, or feel free to read the papers. And I'm switching the topic a little bit, but also extremely relevant. You can print this plastic. A lot of people ask, is this phenomenon reversible? Simple answer is not that reversible. You guys heard me talking about it, right? You always prefer the permanent shape. And every time if you want to program a new temporary shape, you have to kind of manually force it to go into a temporary shape. And then you heat it up, it goes back to the permanent, the end of the story. That's often the typical way people use shape memory effect. That's also how we use it in the self-folding flower. The rose, once folded, cannot flatten itself automatically. So in that sense, it's not quite robotic, right? It's self-folding, it's self-assembly, but it's not so robotic. It's not so reversible. It's not even an actuator in a precise definition. So this video I just shown here is sort of one method, one potential method to make a shape memory polymer reversible. It's actually, again, just an accidental discovery in the lab. So if you try to print, again, just PLA filament, normal PLA filament on a piece of paper, you can actually create a bilayer structure that can bend up and down reversibly. I'll show you the phenomenon and we can discuss why this happens. The video you are showing here is just back then an Ultimaker, but really any FDM printers printing a single layer filament on a piece of paper. This paper is just normal copy paper. And this is just a microscopic photo of the traces. And this video shows once you take it off and take it off from the printing bed, actually it started to bend. And this is a reversible phenomenon. And this shows how it's reversible. So the only maybe slightly high-tech part of this process is the filament we are using. I said it's a PLA filament for the property of shape memory, but maybe you guys notice we're using an alligator clip. So we're actually pumping in current. So this filament has some graphene particles in it. So it's conductive. It's a conductive PLA filament. And we didn't make it by ourselves. You can get it off the shelf. It's slightly more expensive than just pure PLA filament, but you can pretty much buy it online. And now if you pump in current, it's due to resistive heating. So the filament traces will heat up. And once it gets softened, if you remember what I said, once it gets softened, the filament tries to contract, right? So it tries to contract, but the paper does not. That's why the filament will pull the paper upwards, and you can see a bending effect together with the paper substrate. To, but then what is happening is interesting. So once you turn off the current, you are cooling down the filament, right? But now the paper is playing a role. Paper also is kind of elastic. It's also kind of shape memory. Paper tends to go flat. If you just let a piece of paper stay there, it automatically go back flat. So this is what's happening. So there's a counterbalanced forces. They are always fighting each other. It's kind of a chess game. So when you heat it up, the filament pulling the paper up. When you cool the filament down, the filament is, the shape memory is not behaving perfectly. Now the paper gets stronger and the paper is pulling the filament back. It's a very intricate relationship, as you guys can imagine. So the thickness of the filament does matter. If it gets too thick, the paper gets too weak relatively. So this phenomenon is not happening. But anyway, if you tune everything right, you can do something quite interesting. So for example, you can play with different geometrical patterns by basically printing traces of different shape. You can get interesting morphing behavior volumetrically, and you can also do some cut in the piece of paper and only print the filament at specific locations to do kind of a morphing origami structure. You could also try to tessellate the structures. You can, like Lego pieces, right? You can combine multiple bending actuators in specific way to get even more interesting pattern effect. And this is, maybe some of you guys played with this. This is a pop-up origami. As a kid, you open a book, you see something pop up. And a lot of them are origami technique. So here, if you introduce this a black filament, you can make an animated pop-up origami. Yeah, so unlimited creativity, you could also introduce the bending actuator in the center of a passive frame to have this sort of a shearing effect, right? And you can also tune the permeability if you try to arrange two pieces of the bending actuator face to face. And I mentioned those filaments are conductive. So certainly you can try to use those filaments beyond heating for sensing. So here you can see the filament. Once you touch it, it can sense. It's like a button, right? And also it kind of sense your pressure. So if you press harder, the bubbles on the background will increase its volume. And you can also use as a slide sensor. So if you are more of an electrical engineer, you know this is a very straightforward trick, but basically you are changing the resistance between your body and also the printing filament. This was also just some toy demos to show you can combine them and make them functional. You can make grippers or build some robotic toys. So morphing matter is always a interaction of the material property and also the structure and geometry. That's why it's a very designer-friendly topic, because a lot to do with the structure design. When I say designers, broadly covering architects, right, product designer, mechanical engineer, let's say. Yeah, this was a fun demo. It's a synthetic mimosa, since we were on the topic of artificial plant. When you touch the leaf can automatically close. And if you guys know mimosa, it's actually, yeah, it's a very classic plant responding to human touch. You can also make a lampshade. They can go straighten to change the shape of the lampshade and such, so the lighting pattern. And this one was using a Doodle Pen. There is a thing called Doodle Pen. It's basically a handhold 3D printer. And you can draw. As a kid, you always draw, right? But here you draw a shape, the shape can pop up and animate. And so the leading researcher on this project ran a workshop over the summer. And he ran the workshop with a group of graphic designers to understand how the empowered paper, let's say kinematic papers, can help them to think about novel book design or graphic design. So these are some of the outcomes. And even if you don't get this conductive filament, you could also get a very similar reversible transformation effect by just printing normal PLA on a piece of paper. But because the filament is not conductive, so you cannot use electricity to circuitry to control it, right? But you can still blow hot air with a hair dryer, for example, turn off the hair dryer to see this alternate actuation effect. To get a little bit deeper than what we managed to dive into before. So it's in the lab is also one of the main topics, at least in the past. We are kind of moving on to some other materials nowadays. But for a while, we kept pushing the limit of what this very accessible technology can do. So I showed you guys the self-folding flowers, and then printing on piece of paper, so it becomes inversible. And later we also tried to push some of the other form factors, basically the geometrical space of this project. And Genja showed you guys some of the algorithm side of things. So there was always this hidden principle. So when you think about designing more sophisticated morphing behavior, you started to really get into the concept of geometrical computing. So in the lab, there are often the collaboration between computer scientists and also designer. The designer broadly defined as people who do physical things. They could be material scientists, right? They could be a product designer. But anyway, so there's always this hidden force you need to deal with. That is more physical science, but then you also want to compute, right? You compute how things deform, how to map to shape states. Those are quite of a geometrical problem, but it's of course also a physics problem, because anything involving stimuli, energy stimuli, and transformation is to do with force. So in terms of the shape space, I'm not sure if you guys noticed, most of the shapes are flattenable. So in a sense, it's a piece of paper. I unfold it, it can go flat. Geometrically speaking, those are called developable geometries. They have zero Gaussian curvature. But there are also more interesting shapes, especially to graphic people. So those are called non-developable shapes, and like a bow, or like our face. So those you can't easily flatten it, right, without purposely stretching it. So those shapes are much harder to morph, as you guys can imagine, because you need to induce inherent material stretch or compression. Basically, you need to not only do folding, but also you need to deform and stretch the material. So that's much trickier. And we also tried different ways to tackle this. So for example, if you want to make a bow, again, you can't easily flatten it, but you can simplify it into mesh. And then you can change the contraction ratio of each beam of this mesh. And that way, globally speaking, you can tune the morphology. So for example, this chair surface, this is a 1-to-1 scale. I was able to sit on it. The legs were not morphed, but the chair surface was morphed. So we printed the structure flat, and the color on the left actually indicates the shrinkage ratio. So the blue parts shrink less and the redder parts shrink more. And if you dip this flat shape into water, you can see it morphs into a pre-dictated shape. And as you can tell, it's a mesh, but still it's a smooth surface, and it's kind of like a bow. And you can do interesting shapes like this one, from a flat disc turns into a fruit plate, or this one is an armor again. So they were all printed flat, just like a flat grid. This was a collaboration. So an industrial designer did a 1 semester independent study in the lab, and he proposed the idea of making a shoe support. He basically modified his own Nike shoe and printed some flat grid and trigger them in hot water and wrap around his own ankle for basically like a stiffer support for hiking, for example. And talking about these more interesting shapes, and this is what I said, right? So they all, they can't be straightened without being introduced internal stress or deformation. Like the bow, like the dome, the top of the dome, and a lot of actually surfaces on living things like animal or human beings are all non-developable surfaces. And I believe Genja, I'm not sure how much he mentioned about it. So there are interesting ways to define the printing path to get also a non-hole geometry to morph into more interesting non-developable shapes. So for example, instead of just doing straight printing path, if you try to print in this concentric circle fashion, basically you can induce a shrinkage along the circles, right? Along the circle direction. So each ring will shrink. And as an accumulated result, this will pop up into a dome. This is just a simulation to show the result. Here, the color also indicates different shrinkage ratio. So the idea is you can also control the shrinkage ratio. You can certainly print the disk uniformly shrink with the same ratio. But once you tune the shrinkage ratio, you can get even more interesting center symmetrical shapes. So you can see the previous one more like a, what you call it, this pointy tip shape, right? But versus this one, this looks like a dome. And if you guys want to get into the kind of the geometrical calculation part, is also quite straightforward. So you have a initial original length, and then you know how much each circle will shrink, and then you can basically deterministically calculate what is the profile, the side profile once it's morphed. Again, if you see the color just as shrinkage ratio, and depends on how you distribute the shrinkage ratio, the print paths are the same. The print paths are all just concentric circles. But if you control how each circle shrink, right, how much each circle shrink, you can then turn the same looking disk with the same print path into different 3D shapes once you heat them up. Again, this gets a lot more sophisticated from there. I started to feel 4 minutes is not realistic for me to really explain everything. But again, papers are attached at the bottom. Definitely feel free to check our website very briefly, and don't get stressed if you cannot follow. So later, we started to think about arbitrary surfaces. What if it's not a center symmetrical dome, right? What if you want to morph a human face? And here, what you want to do is you really want to control the shrinkage ratio, not only per circle, but per point per se. So you want to be able to control the shrinkage ratio more in a discrete math sense. So you wanna control the shrinkage ratio at each and every single point, pixel, voxel, if you will. So you can actually control the arbitrary shape morphing. So Jianzhe figured out a way to do it. So it turns out, which is actually physically very, very interesting as well. I'm not talking about the total thickness. I'm talking about each individual layer thickness. It turns out each individual layer thickness can dictate the local shrinkage ratio. So if you print much thinner individual layers, it will shrink more. If you print thicker layers, they will shrink less. Shrink less is shown on the left, and shrink more is shown on the right. Again, if you're interested in the physics, that's just because if you print thinner layers, think about it, it cools down faster. If it cools down faster, it locks the polymer chain in more straightened mode. So when you heat it up again, it'll show a stronger shrinkage effect because it tries to bounce back to the random chaotic polymer arrangement. Anyway, yeah, now you just need to understand that we can control locally the shrinkage ratio and each and every spot. And then use a data-driven method, you can start to quantify how the layer thickness, individual layer thickness, not total thickness of your structure, corresponds to the shrinkage ratio. And then you can plot this into your algorithm and really start to design a shape that has arbitrary shrinkage ratio at each local region. And now you can do a little bit more interesting shape, right? You can combine things together, like all the principles I mentioned together, to form more interesting shapes. And you also need to solve this numerically with some smart method. So, but the line you are seeing here now are getting more sophisticated. So the color, as you can see visually, right, the color gradients gets a little bit out of control because these are not generated by human being anymore. These are by computer. And then you can basically analyze a 3D shape like a bunny, sorry, like a teddy bear. And based on the local curvature, you calculate what is the shrinkage ratio needed if you want to flatten it, or if you want a flat shape turns into this 3D shape. And that's why you see the third and also the fourth teddy bear looks like very colorful, and also the color distribution are corresponding to the local curvature of the teddy bear. And eventually what we can do is we can generate the print to path and export it into a 3D printer, print it out flat, and then you can get a 3D shape morphed. And left hand, this is a Hawaii island. You get the 3D data from Google Earth, and then you can flatten it, print it out, even do some screen printing to get the right color you want. That's one on the left. And once you trigger it, it shows like a hill on the right hand. And you can now do more arbitrary shapes. I will stop here. But again, this is I think it's a very interesting paper to read in a greater depth if you are more interested in the kind of computational processing aspects of morphing matter.